Hi folks, we're on the very last section of the book. It's kind of exciting. 17.8, the Divergence Theorem. Um, Before I just leap into the theorem, I wanted to kind of spin a little story to motivate what's going on here. And this has to do with the concept of boundaries. What is the boundary of different sorts of regions? So if you have something that's one-dimensional, like a wire, well, if it's unbounded, it means it keeps running forever, which is hard to do if it's actually made of something. But if it's bounded, it means there's an end. And I guess I picture this as if I'm something that lives on a one-dimensional track, like maybe a train, for instance, is this sort of thing. I might be in here moving around, exploring my one-dimensional space in different ways, but there comes a place where if I keep going, I would sort of exit the space I've been living in. And when you hit that frontier, that place where you would leave the track that you've been riding on, that's weird if you're a train because you really can't run if there's no tracks, but you get the idea. There's an end to the track. Well, so in the 1D case of like something like a wire or a set of train tracks, the boundary is 2 points. I made it curvy. Usually we just see this is an interval. There's a straight interval and it's got 2 endpoints. So a 1D thing, those 2 guys are the boundary. What if I've got something 2-dimensional? Well, that's a region in the plane. This is the kind of thing we dealt with in Green's theorem. But I mean the interior of that loop I just drew by saying the 2-dimensional thing. Most of us human beings live on what essentially is a 2-dimensional surface. We don't get off the surface of the Earth very much anyway. A couple of inches in my case, maybe a few feet in some of the younger people's case. Unless you're a pilot or something, then you can move 3D. But most of us live in a 2-dimensional world, and there actually is limits to how far we can go. Well, they're practical limits rather than honest limits. But let's think: is there a situation where we're on a 2D world and there's really a boundary? How about if you're at an ice skating rink, or this is a frozen pond out in the woods, and you can skate around on the frozen pond, but you get here and you hit dirt instead of ice, and you can no longer skate. Now, the cleaned up version of that picture in 2D is something like the unit circle, where the interior is called the disk, and the boundary, in the topologist terms, this is called S1. It's the first sphere there is. Actually, that's S0, the 0-dimensional sphere, because it's the boundary of something that's 1-dimensional. And this is something to start paying attention to. The dimensionality of the thing versus the dimensionality of its boundary. The thing here is 1-dimensional. The boundary is a pair of points. Points are 0-dimensional. Here the ice rink is 2-dimensional. The boundary, though, is this interface between the ice and the land and the ground outside, and that's a 1-dimensional thing. It goes around in a circle, but still any piece of it looks like a little bit of a line. Well, working up into 3D, and this is definitely hard for human beings to think about. But if I'm in 3D, imagine you had something that looked like, say, a giant peach. That's a solid thing. The interior of it is the solid object. What's its boundary? Well, imagine you were like a worm or something living inside the flesh of this giant peach. You run around through there eating peach, but if you go too near the surface of it, you may exit the surface of it, and now your little worm head is sticking out of the solid thing. You've just found the boundary, in other words. So that, I don't know, I think I've just reversed the usual convention is that if a path is not visible, you make it dashed. So that should have been the worm while it was eating through the peach on the inside, and then it becomes solid looking once it emerges from there. That's the way we normally would draw that. Sorry, that was kind of confusing. But anyway, what is the boundary of our solid region? It's a surface. So here the boundary, it's a little bit hard to point to, but boundary is a surface. And if I was making something, a cleaner example that didn't look like a giant peach, but sort of followed this progression, well, the physical body is a ball. What's the surface of the ball? That part on the outside, the skin of the ball, that's known as a sphere. And that actually, in topology terms, is called S2. But it's really it's the first example of a sphere. And so the two-dimensional sphere is what we always mean by a sphere. S1, as a name for a circle, is saying that's the one-dimensional version of a sphere, and S0 for that. There's even S3, the three-dimensional version of a sphere, and that's the surface of a four-dimensional ball. Good luck trying to visualize what that is, but you know it can be done, in fact. And that's a crude introduction to topology. Actually, that's one of the big subjects that people study in topology is the dimensionality of objects, and then their boundaries is a big idea too. And it's generalizable up into higher dimensions, so you can have things like the four-dimensional sphere that bounds a five-dimensional ball, things like that. All right, so where does this stuff pay off in terms of calculus or an understanding of the calculus? When we had just a one-dimensional thing with its endpoints, we had the fundamental theorem of calculus, which said the integral over that region of some function, because this is A and this is B, right? That thing can be got by finding an antiderivative of the function and evaluating at the two endpoints and subtracting. That's the notation we use for that. The point is, the integral is happening on the inside of the region, and the antiderivative gets evaluated at the boundary of the region. When we did this kind of stuff for Green's theorem, we had the region, R, was this sort of interior of a disk, or something roughly shaped like a disk. And then the boundary was this curve on the outside. And then Green's theorem said, well, it said two different things, but the one I'm going to focus on for today is the divergence form of Green's theorem, and then it said a double integral over the region of the divergence of the vector field with respect to area could be done instead as an integral on the boundary. This subtraction is also an integral of a certain type, but the integral on the boundary there is a closed integral actually over the curve C. What did we do for this kind? We did the normal flow or flux of the field, so that would be F dotted with N ds. I guess I'll say it that way. Still, one thing happening on the interior, another thing happening on the boundary, and you notice the interior thing is more complicated. It's a double integral. The boundary thing is less complicated, just a single integral. Here the interior thing had an integral in it, and the thing that you do on the boundary doesn't even have an integral sign. And there was this other version of Green's theorem, and that led us to a generalization of Green's theorem, which we just did, Stokes' theorem. But I want to follow this through one more step in this sort of progression up in terms of dimensionality of the things. If we have a solid ball, I guess I call it B for ball, and the boundary of it is the skin, so to speak, you know, the outer part. That's a surface, S. And this thing we're about to do, the divergence theorem, basically is the same thing, just popped up one in dimensionality. So instead of a double integral over a region, we need a triple integral over a 3D volume. So it'll be integral, integral, integral over B. It's still going to be the divergence of the field. But of course, we're in a triple integral situation, so it wouldn't be differential area, but rather differential volume. And that is equal to, well, it's similar in that we go from, a more complicated integral to one layer less complicated. A 2D integral here became a single integral there. 3 integrals is going to turn it into 2. Now, some people will decorate this thing like so. And that's sort of in solidarity with this notation. This was saying that the integral goes all the way around C. And this is saying the same thing for the surface of the ball. The integral has to go over the entire surface of the ball. But it's the same integrand, except that it's now 3-dimensional. It's the function, the vector field, dotted with normal vectors for the surface. And then, this changes because this was done with respect to arc length. This guy's going to be done with respect to surface area on the surface. So it's not confusing if I use S for surface area, the differential surface area, and we also have S for the surface itself. Yeah, so that's what you're looking at right there is the divergence theorem. You see the parallelism here? We've gone from something 2-dimensional equaling something 1-dimensional, here it's something 3-dimensional equaling something 2-dimensional. But the things inside are all the same. We're going to need to think a little bit about the meaning of this. I'm not sure if I've done it justice, but I was trying to make a sketch of one of the jet engines dangling beneath the wing of an airplane that's in flight. That may be the worst airplane caricature of all time. But it's okay. We're gonna look at this just from the perspective of a vector field. And we usually think of the atmosphere of the planet sitting still and the airplane is traveling through the atmosphere, but I want to kind of reverse the roles there. Imagine the airplane is kind of fixed in space and the air is passing past the airplane. It's kind of a change in perspective, really. Most of the places, at least far from the engines, the air is just flying along at a steady 500 miles an hour. So there's all these vectors that point towards the tail of the airplane that are 500 miles an hour long. But the vector field near this engine has a little bit different characteristic. First of all, there's a fan or a turbine in the front of the thing that sucks air in. So the air here might be going 500 miles an hour, but the next packet of air that's a little closer to the engine is going appreciably faster. So that's meant to be a longer vector. This one's 500 mph. This one's maybe 700 or 800 miles per hour. Let's say 7. And that alone, by the way, that suction, pulling the air in, that partly is what drives the plane forward. But a bigger component of the thrust of the jet engine that makes the airplane go is that the air that exits it is going appreciably faster. A lot faster, in fact, 1,200, 1,300 miles an hour. Depends on the thrust setting that the pilot is using, but it can be a lot. I mean, if in the run-up phase, they call it, the airplanes need to test out their engines before they take off to make sure they can achieve full thrust. Because if there's something wrong in the engine, you want to find out before you go into the air. So they'll do that sort of thing. It's called a run-up. They get the airplane out near somewhere isolated, pretty far from the airport and people and cars and things, and they shove the throttle forward while stomping their feet on the brakes to keep it from actually moving, and they see that they develop the kind of thrust they're expecting. And if people are around at that time, if you are near the the place where the exhaust from that jet engine is facing, it can literally blow you off your feet. It can kill you, in fact, which happens occasionally, which is why they now are it happens rather rarely, but it had happened in the past, and so they always make sure to do that run up in an isolated area. It's part of the reason why airports have kind of a lot of land. That it seems like they don't need all the land they have, but it's because there's dangerous amounts of thrust coming off the back of an airplane that's well, when it's taking off, for instance, or when it's doing this run up in preparation for takeoff. Having flown some private aircraft, I tell you that they tell you to be really careful about getting anywhere near the back end of a real jet, because if you're in something like a Cessna and you get hit by the wind that gets generated by this engine, it's going to flip your airplane over, and it'll be damaged at the least. Anyway, so that's the idea. We've got an interesting phenomenon. If you look at a volume or a surface that includes this stuff here, and think about all the vectors that are coming into and leaving this surface. And I've drawn that, obviously it's a circle on the board, but I want you to think of it like a soap film or something, a surface that encloses this jet engine. There's all these 500 mile per hour arrows coming in to it here. And there's actually quite a lot of 500 mile per hour arrows leaving it here. 500's in, 500's out, not a big difference. But in here, there's arrows leaving that are much longer. So we've got to figure out how to make account of that, because you've got this region in space, volume of space, with a certain amount of stuff coming in and more stuff leaving. How could it be that more matter is leaving this region than is coming into this region? Well, it's only a slight bit more matter, but the matter the flow lines are longer because the vectors are longer because it's going faster. Where does it come from? Well, it comes from in these wings. Inside the wings, there's kerosene, and the kerosene gets fed down into here, and it's set on fire. This is my symbol for fire. It looks like a candle, but really it's not a candle in there. It's a nightmarishly hot spot. There's a lot of sort of hellish flame going on in the inside of a jet engine. It's so hot that the ordinary materials just melt and fall apart if you try to use them inside of a jet engine. The turbines and things inside of a jet engine have to be made out of special alloys called super alloys that are able to resist the temperatures involved. So what's going on is energy is being liberated inside the engine, and that energy is expanding the air. You heat something up, it gets bigger. So what's really happening is energy is going in to make it, the place of matter. But the fact that the gases expand here allows for there to be more going out than we're coming in. That essentially is the whole principle of a jet engine. Not that much comes in, a whole lot more goes out. And well, we could talk about the turbine systems and everything too. That's interesting, but that's more for a course in thermodynamics. I just want you to see that this is a classic place where we've got divergence. There's more stuff leaving than there is coming into this region. So there must be some sort of expansion going on. That's what divergence is all about, an expansion. One way to think about that expansion is I wouldn't want to do this with a real jet engine, but suppose you had a bunch of balloons. A little constellation of balloons. Looks like, how about? Wait, if I do one more, that makes it look like Orion. Is that good? No, I can't draw Orion. That's not sort of the point anyway. There you go. That looks reasonable. I've got the belt, and then two more above. Fine. If you followed those, of course, if it went into a jet engine, it would actually just get shredded. But imagine those points pass through here. What happens to them? They get bigger And they get bigger mostly in the direction this way, right? We'd have a changed version of that thing that was stretched a lot horizontally. Did I make it look like it's bigger? Here it was only about 3 inches apart. Here it's like 6 inches apart. There we go. That's what divergence is about. In a particular region of space, if you have some test points flowing through there, they change their size. They move farther apart. That's something that can happen at any point. In fact, in the jet engine, it happens right in the middle there. But, you know, I guess I could make this bounding surface smaller and smaller and smaller until it was right on the inside core of the jet engine. It would just make the drawing maybe less easy to understand. Yeah, so divergence is the tendency for the material to expand. If you think about it in terms of volumes of air, it's generally how much heat is being applied. If heat is being applied some places, that air is going to expand. If it's cold in other places, that air is going to contract. And that's kind of the essence of predicting the weather, in a way. All right. So there's another thing to think about in terms of the flow of test points like this. This little copy of the constellation Orion. It could have, in the process of going through this region of space, come out on the other side, turned upside down. That would be curl. Right? So there's sort of, I don't know, I sort of like to imagine, like, when I sometimes show pictures of people in primitive areas using these nets that they cast out into a lake or a pond, and they collect up fish. Excuse me. Imagine you toss a net out, and here's the rope that you tossed it by, and so it's a net shaped like that. And a little bit later, it's a much bigger net. The net has expanded. If you see that, you're talking about divergence. If a bunch of test points in the flow move apart from one another, that's divergence. What if you see something like this? You toss that net onto the surface, it's floating, and then a little bit later, it's going downstream, but a little bit later, it's turned. I'm trying to make it roughly the same size, but it's spun around like this. That's curl. If the flow involves making a collection of test points rotate, you're talking about curl. If it involves making a collection of test points expand apart from one another, then you're talking about divergence. Diverging, curling. I can't draw curling very well. They're still moving as well. So it's really a combination of sort of three effects. An object in space can be translating, can be rotating, and it can also be changing its size, either shrinking or expanding. So between the translation, which is the flow itself, the divergence, which is the amount to which the flow is expanding or contracting, and the curl, which is the amount that the flow is tending to spin around, you've got a pretty complete description of the flow in a vector field at a point. All right, so I thought I'd run just an example of this. This is a fairly simple one. The vector field I'm going to look at is the radial vector field, where we've used it a few times. One that looks kind of like an explosion. And just S is the unit sphere, so the three-dimensional volume, of course, is the ball, the stuff inside the unit sphere. But the surface integral we'll do is on the surface, so that's the R vectors that have, well, things in spherical coordinates where the rho is 1. And so this is really just the spherical coordinates thing with the rows replaced with 1s, or effectively erased because they're 1s. All right, so we've seen that a bunch of times, I think, now. So this uses two parameters, the longitude and the colatitude, and gets us a parameterization of the surface of the sphere. Great. All right, so we need to have the two tangent vectors in the theta and the phi directions, respectively. T sub phi, that's take the derivative of your position vector with respect to phi. Sine phi will become cos phi. Cos theta acts like a constant. And that sine phi also turns into cos phi. And that sine theta acts as a constant there. And finally, cos phi, that will turn into negative sine phi. So there's our tangent vector in the direction of changing phi. A tangent vector for the theta direction is, what will that be? Cos theta becomes minus sine theta, so we'll get minus sine phi sine theta. Again, the sine phi in this case is going to be acting as a constant. And this is sine theta, so when we're doing a theta derivative, that acts as a constant, and sine theta becomes cos theta. And lastly, the position vector has a function that doesn't depend on theta in its z-coordinates, so that just becomes a 0 when you're in the theta direction. Which, by the way, that makes sense if you think about it. The theta direction tangent vectors, if you were to imagine yourself on a sphere, there's the North Pole, lines of longitude would be coming down like this. Lines of latitude go that way. And theta changing is following a line of latitude, because it's a vector that points more or less horizontal as you go around. That's a terrible sketch, but I was just trying to give you a crude idea that changing theta should make a thing that has no z-coordinate, or a 0 as a z-coordinate. All right, so we need to get there's two ways to think about this. We're either getting the factor that gives us the translation between area in the theta phi world and area in the surface of the sphere, which is the length of the cross product. Or you can think directly about the cross product of this gets you a normal vector and that factor, or a normal vector whose length is that factor. So in any case, we want to know what is the cross product of t phi and t theta, whichever way we decide to handle that. I suspect, maybe I can squeeze it. It's a big determinant with an I, J, and a K in the top row. And then we're doing phi first, so let me just copy that one in there. Cos phi, cos theta, sine phi, sine theta. No, I skipped over. I gotta look at t phi. Cos phi, sine theta. And lastly, minus sine phi. And then in the bottom row, we'll have the components of t theta. There's a minus sine phi, sine theta. Sine phi, cos theta. And 0. All right, so I'm just going to try to squeeze and get this into coordinate form underneath. The I component will consist of the product that way minus the product this way, and so the first product is 0, and the second one it's negative of that, so this one minus sign gets canceled. What we've got there then is sine phi times cos theta, or sine squared phi cos theta. You get the J component, this is the one where you go around the edge. So it'll be minus sine phi times sine theta, and then minus is 0 on the other direction, 0 times the cos phi cos theta. So the two minus signs cancel, and we end up with sine squared phi and sine theta. And what about the z coordinate? At that, I'm feeling like I maybe have not got enough room for, because that's going to involve the cross product of these two, well, that x business of these two things that are kind of longish. Yeah, so I definitely haven't left myself enough space here. Let me move up to the top of the board and get that whole cross product written out. So this is t phi cross t theta. Those are the tangent vectors. That's equal to sine squared phi cos theta. Just copying so far. Sine squared phi sine theta. And then I'll move down for the last piece. That one times this one. What is it? There's two cos thetas. There's a cos phi and a sine phi. So I believe that's cos phi, sine phi, cos squared theta. Cos squared theta. And then these two, double underline these, product of those subtracted, right? So do you see how there's one minus sign amongst them? But we're subtracting, so that'll be plus. And then what are the total of it? There's a sine phi, a sine theta and a sine theta, and sine phi and cos phi. Oh, those are partly the same as what we had in the first one. Wait, let's write it in the same direction. Cos phi, sine phi, and sine squared theta. Now that actually simplifies a good bit. You might not spot it right away, or perhaps you do. Cos phi, sine phi, and cos phi, sine phi, those guys are in both terms here. And apart from them, we've got a Pythagorean identity. So that part, that whole z coordinate simplifies to just cos phi, sine phi. You can imagine factoring out these parts that I put the squiggles under, then what would be left would be cos squared theta plus sine squared theta, which is 1. So let's look at it again. We've got sine squared phi cos theta, sine squared phi sine theta. And do I have enough room on the same line now? It's cos phi sine phi. Yeah, all right. Can we do anything else with it? Well, as a matter of fact, I think there is one last thing you can do. There's a sine phi, at least one copy of sine phi in each of those. So pull that out as a scalar function times the vector. And then what's left is sine phi cos theta, sine phi sine theta, and then cos phi. And that last vector that I've just written down seems very familiar to me. Does that seem familiar to you? It's the spherical coordinates parameterization. Sine phi cos, I'm reading it from the book now. This is what I'm looking at on page 1054. I've got this table that has the spherical to rectangular. Sine phi cos theta, sine phi sine theta, cos phi. That's our guy. So if you care about the length of this part is length 1. Right? And I mean, you could go ahead and take do the square root of the sum of the squares if you want, or you could just recognize it as being the spherical coordinates parameterization. So it's radius 1. I don't know, do you guys feel like I should do the hard work? Let's do the hard work. So we want the square root of the sum of the squares, so that would be sine squared phi cos squared phi theta, excuse me, plus sine squared phi sine squared theta plus cos squared phi, all of this to the 1/2 power. What can I do to simplify? You see the first two terms have cos squared and sine squared in them? So you're looking for a Pythagorean identity to simplify that? Yeah, it's perfect. The other thing they have in them is sine squared phi. So this is equal to the first two terms combined to give you just a sine squared phi plus cos squared phi to the 1/2 power. And finally, that's 1 to the 1/2. This is 1. Like I said. So that means the length of t phi cross t theta is just this extra factor that we have on there. Sine of phi. Well, now technically, it's the absolute value of the sine of phi because, you know, sometimes sine of phi will be negative, and then the length of a vector is never a negative thing. But where we're going to be working, phi runs between 0 and pi, or between 0 and 180 degrees. So think about the value of sine phi when phi is between 0 and pi radians. And that's the first arch of the sine function. So you don't need those absolute values where we're working. Just say sine phi, because phi is in this range. Okay, so we should have everything we need now to do the surface integral that's in the divergence theorem. Yeah, because it's just sine phi. I think I can erase this and I won't forget that. All right, let me leave that on the bottom just in case I have a brain failure. What we want to do is the closed integral over the surface of the sphere of the vector field dotted with a normal vector times ds. I should be more careful about my s's. That's a capital S for a surface element. Little s is for line, what do they call it? Arc length parameterization. So, and n is really easy, and f is really easy in this case because f is the vector field xyz, and n is also the vector field xyz because, well, I mean, just think about the geometry of this. If you're at a point on the surface of the sphere, that vector xyz gives you your location on the sphere, and the same vector gives you which way is out, you know, the outward normal on the sphere. So so that's just the length of xyz dotted with xyz. But if we're on the sphere, what is that length? Yeah, both vectors are of length 1, so the dot product is length 1. They're parallel to each other, and they're. I guess that feels a little cheaty, like I'm using the geometry to tell you what the answer is. But well, here's what the answer is really going to be. You're going to integrate 1 times the ds, which is this factor, sine phi, times d theta d phi. And I don't know which order those go in yet. We can decide that. Should it be d theta d phi or d phi d theta? Well, the inside of the integral has a function of phi, so maybe it's most convenient to integrate with respect to phi first. If we're integrating with respect to phi first, then this guy is 0 to pi, and the theta goes from 0 to 2 pi. The point of those limits is to go all the way from the North Pole to the South Pole in terms of colatitude, and completely around the sphere in terms of longitude. So I had them wrong here. I should have had phi and theta. But I feel like we want to probably see why that's 1 without just appealing to a geometric sketch. So remember that f is xyz, was the example I started with. But what are xyz if you're on the surface of the sphere? It was given parametrically by those equations. So that's going to be sine phi cos theta sine phi sine theta and finally it's just cos phi, right? Yeah. Now, the idea that the normal vector is just the same as your position vector, that I think I'm just going to say, yeah, we can work that out. Although the normal vector, actually the computation of t phi cross t theta gave us this unit normal vector scaled by the length of sine phi. So it was something we actually already calculated. But if I just pull out the n part, the normal vector, it turned out, remember what it was? It turned out to be the same thing as the position vector. And if I do f dot n, well, we already did this, really, because f dot n is the square of the lengths of the two things multiplied. Sorry, I just said that wrong. It's the sum of the squares of the components, because the components are equal. So f dot n is sine squared phi cos squared theta plus, that's from the first times first, plus sine squared phi sine squared theta plus cos phi times cos phi, or cos squared phi. And, whoops, not a vector, that's just the dot product. So we did this previously and saw that that computation gives us 1. Cool, so this is correct. That 1 is correct. Can we do the integral? Sure, you integrate sine phi and you will get negative cos phi evaluated between pi and 0. So we have negative cos pi minus negative cos 0. Cosine of pi is actually minus 1, so this is plus 1, and that's plus 1. So this was just me evaluating the integral of the inside thing. So we still need to do the integral from 0 to 2 pi of that, which was 2, with respect to theta. All right, well that's just going to be theta evaluated between these limits. It gives us 2 pi. So the final answer is 4 pi. Cool. 4 pi. That was doing the closed surface integral. What about the triple integral of the divergence of our vector field? with respect to volume. Well, first let's figure out the divergence of the vector field. Del dot f, remember the field was x, y, z, so the x derivative of it is 1, and the y derivative of the y coordinate is 1, and the z derivative of the z coordinate is 1. So del dot f is equal to 3. Wow, that was quick. Remember the surface integral just went crazy, but we just turned this into, we're going to integrate, triple integrate over the volume of a sphere, 3, with respect to volume. So in other words, we get 3 times the volume of a sphere. 3, and the volume of the sphere is 4/3 pi r cubed. Our radius is 1 in this one, so 4/3 pi 1 cubed. The 3's cancel. 4 pi, 1 cubed is a 1. Okay, yeah, it's 4 pi. You see, you got the same answer in both ways. And this is sort of typical of both Stokes' theorem and divergence theorem results, that one or the other will be really easy to do, and the other would be really hard to do. Sometimes even impossible to do. You can have surface integrals that you couldn't possibly get. I mean, maybe not literally impossible, but it's so hard you wouldn't want to try it. And solid integrals that are just that easy. You end up integrating a constant over the volume. I want to close out by kind of replicating a chart that's at the very end of 17.8. It's on page 1179. So you can refer to this if you want at 1179, although I'm going to do a little bit extra than what's drawn there. So the point is to sort of get you to see the parallelism between all the different theorems we've created. The fundamental theorem of calculus, of course, very familiar to us at this point. The big idea here is that you've got an interval over which you're integrating the function, but when you find an antiderivative, capital F for little f, you just evaluate at the endpoints of the interval, boundary of the interval, A and B. The fundamental theorem of line integrals is for the situation where you've got a vector field that is the gradient, a vector field that is the gradient of some scalar potential. So the blue lines here are supposed to be some scalar potential. The vector field points uphill along these lines. So there'd be a whole bunch of vectors. You really want to have vectors all along the line to do. But what we integrate in that case across the interior of the line is the vector field. Well, let's call it what it is. It's the gradient of some scalar potential dotted with a tangent vector with respect to arc length. That's done over the curve. C is the black line I've drawn there. But you can just say, look, it's a conservative field, so it doesn't matter what route you take from A to B. All you care about is the change in the potential. So it's the function phi at B minus phi at A. And I think when we first did line integrals, we pointed out how these things were quite similar, right? Next was a bit of a leap, Green's theorem. I've gone ahead and wrote Green's theorem out before we proceeded on, so it'd be good to outline these things or something. There's the fundamental theorem of calculus. Here's the fundamental theorem of line integrals. And then here's the two different versions of Green's theorem. That one and this one. And let's just quickly work over that. In the one on the right, the flux version, you're trying to find flux, which is the same idea as flow across. That is, these little vectors that point across the boundary of the region. And that is related to the extent to which the flow expands inside the region. It's really the divergence of the flow, although, since we're just in 2D, that expression, the x partial of the x coordinate of the field and plus the y partial of the y coordinate of the field, fx plus gy, that gives you the extent to which vectors are separating on the interior. The reason flow is crossing the boundary is that material is coming into, is being born inside of here. There are sources, or there may be a distributed source of flow of water, of material into the inside of that region. But the takeaway is that an integral around the boundary is equal to an integral across the interior. I should have probably said this is the boundary curve C, and this is a double integral across the region A. The circulation or flow version of Green's theorem is this one, where, remember the funny term g sub x minus f sub y, that's the k component of curl. And if your flow is actually two-dimensional, it only has a k component. The curl vector that you compute is going to be perpendicular to the xy plane. Anyway, the thing you should picture is this. There's a sort of a tendency to spin around inside the interior. At every point on the interior, you can calculate an amount to which the vector field is kind of rotating stuff. And if you have a whole bunch of those things, now truly, I'm drawing them as if they were little whirlpools or something, but they're not really. What they are vectors that point out of the surface. That's, they're vectors that point towards you here. And the more curly, more spinny this is, the longer that vector would be. Anyway, all this vorticity that's being added to the medium I would like to think of it as an actual physical medium that's flowing along vector lines. All that stuff that's happening on the interior can be measured or can be realized by a flow or a circulation around the boundary. Well, that's what we're seeing here. The circulation integral, or the circulation is the path integral that's closed around the boundary curve C. The field dotted with tangent vectors. That's, so I was trying to think of these things as being the field vectors, but in fact, there's also, at the same points, there would be tangent vectors that point in the direction of the flow. And it's this dot product that tells you to what extent does the flow line up with the tangential direction, and thus gives you a large number for that circulation. Yeah, but that integral across the boundary of the region is the same thing as the integral across the region itself of the curl. It's sort of all these little things added together. Again, inside the region, on the boundary of the region. Now, these last two guys have their generalizations up into higher dimensionality. The curl version, not really that much higher. It's just kind of lifting the picture up into something that's a distorted version of itself in 3D. But the flux version, it's an honest shift up in dimensionality. And unfortunately, I would like to be able to spread this out the way it was flowing downward, but I just don't have the space. So what we're going to see on the left, a continuation or a generalization of Green's theorem, is Stokes's. And on the right, a version of the, not a version, but a generalization of the flux form of Green's theorem up into higher dimension, into 3D, and that's the divergence theorem. Now, basically I want to take this flat picture and lift it up here and try to draw it in perspective. But I don't want you to think that the base curve C is something that lies in a plane. So I'm going to try to make it seem like, okay, here's a planar curve C, right? But I want the base curve of my the thing that corresponds to the C up here to be something that lies up, that this is the shadow of it, but it's more interesting looking. It goes low, it goes high. Oh no, whoops, it doesn't go out there. It goes like that. So it's got, its shadow may be this nice looking ellipse, but it's really not flat. It's not a two-dimensional thing. It's up there in 3D space. And if you like, think about it as this is the shadow of a roller coaster, and our curve C is the roller coaster itself that's going up and down as we move around. So there's C, the blue thing. And C is the boundary of surfaces. There's many surfaces. Let's sort of imagine throwing a big tent onto this whole thing. So there's an inflatable tent, and I guess we can't see the ones that are going into the back, but there'll be lines in the back that are coming down towards, hooking it to the back side of the roller coaster. I'm not sure how well this diagram is working, but in any case, there's a surface, and C there is its boundary. And Stokes' theorem says that we can do an integral over the boundary or an integral over the surface, and we'll get the same result. Of course, the things have to be appropriate. So on the surface, that's a double integral over S. We're going to integrate the curl of the field, which is now in 3D, you can just write it as del cross F, dotted with respect to surface area. Let's say that dot n ds. But we can also, and often this is much simpler, often we can just go around the boundary, the C, and that'll be a closed path integral around C in 3 dimensions now. And what we're going to need there is the circulation. Really looks rather like this, doesn't it? In fact, the easy or compacted way to write it is FDR. But same thing. Interior of a region on the one hand, boundary of the region on the other. Finally, the divergence theorem. This is harder to draw specifically because in the divergence theorem we're dealing with a solid object. So I'm going to try to reproduce a picture that was in a science book that I had as a kid. It was a split open view of the Earth. And you could see the core of the Earth down on the inside. Right? And the mantle was in here. That shows you the crust and really close to the surface. Actually, the crust of the Earth is only like between a few miles and a few hundred miles thick. So the scale is all wrong on this. But the idea is, I'm trying to give you the sense that there's depth to that thing. And there's a difference between this interior ball and this exterior surface. But this looks exactly like the Green's theorem flux version. We're going to have an integral over the surface of, okay, it doesn't look exactly like it because we have to extend this to 3D, but integral over the surface, and this is a closed integral because it goes over the entire surface of the gradient, or sorry, the divergence of the vector field, del dot F. On the other hand, that can be, what have I done wrong? I've done that wrong, sorry. That's what's on the right-hand side. The thing that's integrated in the surface area is to what extent does the vector field poke out in the normal direction. You've got normal vectors and you've got field vectors, and you want their dot product. F dot n ds. Make sure that that's a capital S because it's a surface area element. And that's equal to, here's where the divergence comes in, del dot F. That would be dV. But again, the high level perspective is you've got an integral across the full thing is equal to an integral on the surface of the thing, on the boundary of it. The ball be the sphere S. Well, that is where we're stopping. That is literally the last thing in the last chapter in the book. So congratulations on making it this far. If you find this stuff confusing, believe me, you're not alone. This is hard math, and I'm really proud of you guys for getting to this point. Where you will see this, if you really want to nail it down and truly understand these theorems, these vector calculus results, take electricity and magnetism in the physics department. Once you really understand Green's theorem and Stokes and divergence theorem, electricity and magnetism turns into an easy course because you've got the hard part done. The math is what's tough about it. And the physical intuition that you get from seeing how it explains electromagnetic phenomena is pretty cool. So that's a plug for the physics department. They have some great people over there that teach E&M. All right, we're done. Bye.